Newton, Foundations of Modern Science. Part 1: Introduction and Early Intellectual Formation. The name Isaac Newton is closely associated with the emergence of modern scientific thinking. His work transformed the understanding of motion, gravity, light, and mathematics. Although scientific knowledge had been developing for centuries before Newton, his achievements unified several strands of inquiry and provided mathematical explanations that influenced research for generations. By combining precise observation, mathematical reasoning, and theoretical analysis, Newton established principles that remain central to science for more than 200 years. The intellectual environment in which Newton worked was shaped by the broader transformation known as the scientific revolution. During this period, scholars across Europe began questioning traditional explanations of nature that had dominated since antiquity. Earlier authorities, particularly the works of Aristotle, had long provided the foundation for natural philosophy. However, by the 17th century, new methods emphasizing observation and mathematics were increasingly influential. One of the most important earlier figures in this transformation was Galileo Galilei, who applied systematic experiments and mathematical reasoning to motion and astronomy. Another major contributor was Johannes Kepler, whose mathematical description of planetary motion provided crucial insights into how celestial bodies move around the sun. These developments formed part of the intellectual context that shaped Newton's thinking. Newton's achievements did not emerge in isolation. They were the result of an intellectual tradition that gradually integrated observation, experimentation, and mathematics. What distinguished Newton was his ability to bring these elements together in a coherent framework capable of explaining both terrestrial and celestial phenomena using the same principles. Early life and family background. Isaac Newton was born on December 25, 1642, according to the Julian calendar used in England at the time, which corresponds to January 4, 1643 in the modern Gregorian calendar. His birthplace was Woolsthorpe, a rural village in the English county of Lincolnshire. The environment of rural England in the 17th century was largely agricultural, and Newton's early surroundings were shaped by farming life rather than academic culture. Newton's father, also named Isaac Newton, was a farmer who died several months before his son was born. His mother, Hannah Ayscough Newton, later remarried and moved to live with her new husband, leaving the young Newton in the care of his maternal grandmother for several years. Historians often note that this separation may have influenced Newton's personality, which later appeared reserved and intensely focused on intellectual work. During childhood, Newton did not initially appear destined for a career in science. However, records from his early schooling indicate that he showed curiosity about mechanical devices and natural phenomena. At the King's School, Grantham, where Newton studied as a teenager, he developed interests that included constructing small machines and experimenting with mechanical designs. Examples recorded by contemporaries include model windmills, water clocks, and mechanical toys. These activities reflected a broader pattern of curiosity and technical experimentation. Although these early efforts were simple compared to Newton's later achievements, they illustrate an emerging interest in how physical systems operate. Mechanical devices were particularly significant because they represented the practical application of principles related to motion and force, concepts that would later become central to Newton's scientific work. Education and intellectual influences. In 1661, Newton entered University of Cambridge, specifically joining Trinity College, Cambridge as a student. The curriculum at Cambridge during this period still relied heavily on traditional philosophical texts. Aristotle's works were widely studied, and natural philosophy was often taught through classical interpretations rather than through experimental investigation. However, the intellectual climate at Cambridge was beginning to change. Scholars increasingly discussed the ideas of newer thinkers whose work challenged traditional frameworks. Among the most influential figures was René Descartes, whose writings proposed a mechanistic interpretation of nature. Descartes argued that natural phenomena could be explained through matter and motion governed by mathematical laws. Another major influence was Francis Bacon, who emphasized the importance of empirical observation and experimentation. Bacon's ideas encouraged scholars to gather evidence systematically and develop conclusions based on observed patterns in nature. Newton began exploring these newer ideas largely through independent study. Surviving notebooks from his student years reveal extensive notes on mathematics, philosophy, and natural science. These notebooks demonstrate that Newton was not merely absorbing existing knowledge, but actively analyzing and questioning the ideas he encountered. Mathematics soon became a central focus of Newton's intellectual development. Earlier mathematicians had developed important tools for studying motion and geometry, but many complex problems remained unsolved. Newton's work would later contribute major advances in this area, particularly through the development of calculus. The Plague Years and independent research. A critical turning point in Newton's early career occurred during the Great Plague of London, which led to the temporary closure of Cambridge University. Newton returned to Woolsthorpe during this period, spending roughly 2 years away from formal academic instruction. Although this interruption might have hindered some students, for Newton, it became a period of intense intellectual productivity. Historians often refer to these years as a time when several of Newton's foundational ideas began to take shape. During this period, Newton explored problems in mathematics related to change and motion. These investigations contributed to the development of what later became known as calculus. Calculus provided a mathematical framework capable of describing continuous motion and variation, allowing scientists to analyze physical processes with unprecedented precision. At the same time, Newton began studying light and optical phenomena. Earlier researchers had examined the behavior of light through lenses and mirrors, but many questions remained about its fundamental nature. Newton conducted experiments using prisms to investigate how white light interacts with transparent materials. These experiments led Newton to conclude that white light is composed of multiple colors that can be separated when passing through a prism. This insight challenged earlier explanations that suggested colors were produced by modifications of pure white light. Newton also began thinking about the motion of celestial bodies. Astronomers had already observed that planets move in elliptical orbits around the Sun, as described by Kepler's laws. Newton started exploring the possibility that a universal force might govern these motions. Early ideas on gravity. One of Newton's most significant contributions was the formulation of the law of universal gravitation. This principle states that every object with mass attracts every other object with a force that depends on their masses and the distance between them. Although the idea is often associated with the popular anecdote about a falling apple, historical evidence suggests that Newton's insight developed through careful analysis rather than a single dramatic moment. Observing falling objects may have prompted questions about gravity, but the full concept emerged through mathematical reasoning and comparison with astronomical observations. Newton realized that the same force causing objects to fall toward Earth could also explain the motion of the Moon around the planet. By comparing the acceleration of falling objects with the motion of the Moon, he concluded that gravity operates over large distances. This realization represented a major conceptual breakthrough because it unified terrestrial and celestial physics. Before Newton, many scholars believed that the laws governing motion on Earth differed from those governing celestial bodies. Newton demonstrated that the same principles apply throughout the universe. Development of mathematical tools. To describe gravitational motion accurately, Newton needed mathematical techniques capable of handling continuous change. This requirement contributed to the refinement of calculus, although the development of calculus is also associated with Gottfried Wilhelm Leibniz. Newton independently developed similar concepts during the mid-1660s. The mathematical methods Newton created allowed scientists to analyze acceleration, velocity, and forces in ways that were previously impossible. These tools later became essential for physics, engineering, and astronomy. Newton's work demonstrated the power of combining mathematics with physical observation. Instead of relying solely on descriptive explanations, he showed that natural phenomena could be expressed through precise mathematical relationships. Return to Cambridge. When Cambridge University reopened after the plague epidemic, Newton returned to continue his studies. His intellectual reputation quickly grew among colleagues and mentors. In 1669, he succeeded his mentor Isaac Barrow as the Lucasian Professor of Mathematics, a prestigious academic position that later became one of the most famous scientific chairs in the world. Holding this position allowed Newton to focus on research and teaching mathematics. During the following years, he continued developing ideas related to optics, mechanics, and mathematics. Many of these ideas would later appear in his major publications. Newton's early career illustrates the combination of factors that shaped his scientific achievements: personal curiosity, mathematical skill, and the broader intellectual transformation of the 17th century all contributed to his work. Historical significance of Newton's early work. By the late 17th century, Newton's research had begun reshaping scientific thought. His mathematical analysis of motion and gravity provided a framework that allowed scientists to predict planetary movements, understand mechanical systems, and explore natural laws with new precision. These developments did not merely influence academic research, they also affected practical fields such as navigation, engineering, and astronomy. Accurate models of planetary motion improved navigation techniques used by sailors and explorers. Mathematical descriptions of forces contributed to advances in mechanical engineering and architecture. The broader significance of Newton's work lies in its demonstration that nature follows consistent mathematical principles. This idea became a central assumption in modern science and continues to guide research across many disciplines.